The question for today is largest divisible subset. Given a set of distinct positive integer nums, return the largest subset answer such that every pair answer I, answer j of elements in the subset satisfied answer I modulo answer j is equal to 0. That means either answer 1 is completely divisible by answer 2 or answer 2 is completely divisible by answer 1. Either or case. That means all the numbers must be factor of each other. If there are multiple solutions, return any of them. The core requirement to solve this question is to be very clear with the basic concepts of the set and modulo. To understand this question, let us revise the concept of sets first. Considering example 1, let us create subset of it, label it, and enclose it inside a universal set. Considering this diagram, we are just going to list out all the subset out of it. Let me make this diagram something more self-explanatory. The first subset will be an empty set, as if we subtract all the subsets from universal set, then we will get 0. That is the empty subset. And it will be followed by all the subsets that we can see from the diagram. If we count this subset, it yields to be 8, that is 2 to the power 3, since 3 elements are present. Now, let us try to understand the second concept, that is of modulo. As mentioned in the question, answer I must be completely divided by or a factor of or a multiple of number 2 or answer 2. So let us see what it is. Consider the example of subset 2 and 3. Here we can see that the remainder of this subset is 1, which is not completely divisible as the remainder is not 0. Hence, we can say that this subset must not be listed in our answer, that needs to be returned. Since this needs to be applied on each and every element, so every subset which is containing 2 and 3 inside it must not be considered while returning the answer. If we eliminate the subsets which contains 2 and 3, we will be left out with 6 out of 8 subsets present, but the subsets that can be returned is only 1, 2 or 1, 3, as we need to return the subset of the largest length. We can return any because it is mentioned in question that any of the two candidates will be considered in the answer. Similarly, let us look at example 2 and see all the subsets of it. And it is difficult to write down here all the 16 subsets. So I am not mentioning all the elements here because it is quite a large element. But suppose that if there are 7 elements, then the subsets will be 2 to the power 7, and the time complexity required will be order of 2 to the power n, which is very huge, that must need to be reduced. Since, as mentioned in the question, we only need to consider the largest subset. So let us see the optimization that we can do here. Let us take another example of 2 to the power 7 to better understand this question and the optimization that we are going to do. To make the things simpler, let us sort the string first, and the sorting does not uh, affect the time complexity here, because the total complexity that we have calculated till now is 2 to the power n, which is quite large than n log n, which is the time required for sorting. So let us sort the string and then list some of the top few subsets that we can write and mention here of 2 to the power 7 2 to the power 7 subsets. So first we will list down the empty set, because if every cell subset is eliminated from the universal set, we will get an empty set. And then we will list down all the numbers itself, as it is always a subset of the superset. And then we will do the pairing. When we do pairing, we see here, we will start from the start, and let us iterate through 2, and we can see that some of the pairs, that is 2 3, 2 7, 2 9, 2 27, they are not factors of each other, hence they are not applicable to be returned as the answer. So we can ignore these. Let us now mention only those sets here which can be returned as answer. Remember that we need to do this iteration over all the n elements, as we need to return the largest, and it is possible that we don't find the largest subset starting from 2. It is possible, as listed here, that the largest subset here we get is from element 3. Let us try to understand this by graph. Let us do all the possible iterations that we did using listing at 2. From 2, we need to transverse all the elements until we don't reach a factor of 2. Once we reach the factor of any factor of 2, we will stop the iteration there. The reason for it is, if we find any number that is a factor of 14, here it means that if 2 is a factor of 14, then any number that will be a factor of 14 means, suppose that we have 28 also, then if 14 is a factor of 28, then from 14 we can find 28, and once we find that 14 is a factor of 28, it is implicit that it is also a factor of 2. That means if we can prove that 14 is a factor of 28, we can also prove that 2 is a factor of 28. Make sense? The largest possible subset that we can find from 2 is 2 and 14 here. Let me make some spaces out here. So Let us iterate through the graph once. Let us say that we are performing depth first search. From 2 we are going to 3. If it is not a factor, it comes back. Then from 2 we are going to 7. It is not a factor, we comes back. Then from 2 we go to 9. It is not a factor, we come back. Then from 2 we go to 14. 2 is a factor of 14. So now we will perform a DFS on 14. From 14 we go to 29. It is not a factor, so it comes back. And now from 14 we go to 27. It is not a factor, so we come back. Now we come back to 2, and the result that we get here is 2 and 14. For better understanding of the question, we will iterate through every element. Let me show you the graph for 3. So now if we iterate from 3, first we will perform a DFS on 3. We go to 7, it is not a factor, and we return back. Then we go to 9. 3 is a factor of 9, and hence now we will perform DFS on 9. From 9 we go to 14. It is not a factor, so we come back. And from now we go to 27. Yes, 27. 9 is a factor of 27. Hence now we perform DFS on 27. We go to 29. 29 is not a factor of 27 is not a factor of 29. Hence we come back, and from backtracking we will see that 3, 9 and 27 are the factors that we get from this complete iteration. The next element is 7. Now let us iterate through 7. When we go to 9, it is not a factor and it comes back. Now we will perform DFS on 14. It is a factor, and now we will perform DFS on 14. We go to 27, it comes back, it is not a factor. We go to 29, it comes back, it is not a factor. And we get 7 as 14 as our answer from this DFS search. The next element is 9. We go to 14, that is not a factor, and return. We go to 27, it is a factor, hence we perform DFS on 27. 27 is not a factor of 29, hence it returns, and the number and the subset that we obtain from this is 9 and 27. The next element is 14. We perform DFS on 14. We go to 27. It is not a factor, it returns. We go to 29. It is not a factor, it returns. And the number that we get is 14 itself. The next number in the sorted list is 27. We go to 20. We perform DFS on 27. We go to 29. It is not a factor, hence it is returned. And the 27 is the number that we obtain here. Next is 29. Since it is the last number, we will directly return it as 29. So now, let us code this DFS transversal. Let us first write the logic for transversing only the first element, and then we can do it for all the elements via for loop. So if it is the so if it's the end of the string, it will return nothing. And then we need to find the match chain of I, and the match chain, if the number is present, the number itself is the match chain. Then we will iterate over all the elements, and if we find that anything is a factor, then we will append it. Otherwise, the then we will append it, and it will become a candidate chain. if the candidate chain is greater than the max chain, that is the number itself, then the max chain will be replaced by the candidate chain and we will return the max chain as the DFS traversal of 2 or for a single element. Now let us perform this for every element, and we will be um, storing the largest subset as empty first, and whatever we get from each iteration we will just compare it and and store the largest subset. Once all the iteration or are over, we will obtain the largest subset and we will just return it. Let us now run the code, and oh, what is this? Okay, sorry, I forgot. It's length, and I am comparing just everything. So yeah, so let me make this correct, and the same problem repeated below. Okay, now let us run this, and yeah, it is working perfectly fine. Let us submit the solution. And oh, time limit exceeded. Only 47 of 49 test cases pass. So now let us see what happened. So this is our graph for every iteration, and can you see any pattern out of it or repeated elements in the graph? Just pause the screen, take few minutes and try to recognize any pattern or repeated thing in the graph itself. I think that you may have noticed it. This There are multiple repeated patterns out of here which can be stored in cache, and if this is present in cache, we must not calculate it for each iteration, rather return those answers from cache itself, and we can save our time for the calculation for these things which are present at the cache. So let us now code it. And yeah, it is working perfectly. Now let us understand the time complexity here. The time complexity shows here is n square, which is correct. One of the n is derived from the DFS transversal that we are doing, and the other from the for loop that we are running. So yeah, it is n square, which is way more optimized. But let us see if we can find any other approach to solve this. So here, as we can see that there are multiple sub-problems out of a problem, and wherever there is repeated pattern or regression involved in any question, the best method to solve it is dynamic programming. Till now, we have done a DFS, we have taken a DFS approach and we have solved the question. Now, we will solve the same question by dynamic programming, or you can say that the method of tabulation. Making a table is not possible here, but let me try to explain the best that I can give. So yeah, so we will be using DP, which will be storing the initial elements. Okay, so let us try to understand this, that we are making a DP, an array in which the initial element is the number itself, because if there is a number, the minimum or the maximum subset that it will contain is number itself. We have seen this earlier. So in DP, with each of the number, we are storing the number itself as the subset initially. Now let us perform the other operations to populate it. As we just saw in the graph that the problems are repeated, and the best way to solve this problem is a bottom-up approach. As 20, let us take this example of 14. Once we calculate what are the subsets of 14, we don't need to calculate it again at the time of 2. We will just append to all the elements of the 14. Or let us take another example, that 29 is a subset of itself. 27 is a subset of itself. When we go to 9, we just need to go to 27 and copy all the elements of 27. The result will be 9 and 27 here. Now when we will calculate the subsets for 3, we will be just finding a factor next to it, that is 3 is a factor of 9. So we will stop the iteration there, and we will copy all the, we will not copy, we will append all the elements that is present at index where 9 is stored and append it to 3. Hence we will get the answer 3, 9 and 27. I hope I am making my best to make you understand. So now let us start from the end. We will check an I and J. For I and J, we can see that they're, they both are not factor of each other. Hence, they, let us move to another, that is 14. When I is at 14, we will iterate J over all the elements after 14, that is 27 and 20. We can see that both are not a factor of 14, hence we will leave 14 as it is and move to the next element, that is 9. Now our I is at 9 and our J will iterate through all the elements. So J will first be 14, which is not a multiple of 9. Then J will be 27, which is a multiple of 9. Hence we will append 27 to, not just 27 to 9. In this case 27 to 9, because 27 is a single element, and once we find any of the multiple of 9, we will stop there our J and we will not iterate it to every element, because if there was anything that was a factor of 27 after that, it would be appended at 27, and we are appending all the we are appending the subset of 27 at 20. Let us now move to 7. 7 is a multiple of 14. 7 is factor of 14. We will move our I to 7 and iterate J over each of the element until we don't find a factor of it. So at 14 our J will stop. Next, our I will be at 3 and we will be moving J until we don't find any factor of 3. So I is 3 and J is first 7, which is not a factor, so we'll move J next. which is 9, which is a factor, so we will append all the elements present at this 9 to 3, that is 3, 9 and 27. Now we will be moving to 2. Once we get to 14, we will stop our j here and append 14 to. I hope that makes sense. Now let us just code it up fast. We will be iterating over every elements in reverse, and guys, you can see that all the steps that I am doing here is just similar to the what we have done is in DFS. The difference is just that we are storing a DP table here and we are doing it in a tabular form. That's it. Now we will be checking now we will be iterating our j and then checking if they are a factor. If they are a factor, then it is a candidate subset. So here we will be returning, here we will be changing the subset at I. And of again I missed the len. Okay, and then we will return the largest subset. That's it. That's it, guys. Pretty much concise code, and yes, the time complexity is same, as only 2 for loops are used, one for the iteration of I and one for j. And space complexity, yeah, for DP we are using. That's it. Thank you, guys. Do remember to like, share and subscribe.